So I had a student today at Calc 2, and we were continuing to work on disk method and donut method and integration. And so if we recall, that's just basically utilizing the area of the circle. I won't go over it all in depth here, but you're basically just taking pi r squared and you're integrating that over your x-axis, right? And you're making these many little disks in order to make a volume. And one way I like to think about that is if you take a chest of drawers, right, and you imagine the surface is like the Cartesian grid, and you just imagine pulling out one of those drawers. So what we're doing is we're often given information in a two-dimensional form, like an f of x, and what we're asked to do is pull that out, right? If this is a chest of drawers here, and we're going to pull that out, so it ends up looking like this. So we pull that out like this, and we end up with a volume. It's a lot like if you ever used SketchUp or one of these graphic apps for architecture. So now what I've done is I've found a volume for that drawer by integrating this shape, the surface of this drawer, over the distance that I pulled it out of the cabinet. And maybe you have a vase of flowers on top, or let's say there's a mirror on the wall, just to make it a little bit more real, right? But that's the idea of the disk method and integration. And this is when it gets really fun. This is when we really start to integrate around spaces and over spaces, and it's a really fun part of math. So the question that he had, which I think is really helpful, it's a good starter problem, is you're given that there's some region, right? And that's going to be the two-dimensional surface of the cabinet drawer. And I've never seen it talked about like this. I think this is a really great way of understanding it. I just came up with it. And you're told that the region is bounded by the first quadrant and by the y-axis, and by the line y equals 4, and finally the curve y equal to x squared. So this is the whole game kind of in Calc 2 in college, or in advanced calculus in high school, is what do we do with this set of information, these words, these variables, and in other words, like, how do we visualize that in the Cartesian grid? So let's just take a look at that. Like, what does this look like? Like, what is this region? So we're told it's in the first quadrant. So we know that's for all x is positive and y is positive. We're in this quadrant here on the Cartesian grid. We're told it's bound by the y-axis. So where is that? So the y-axis is this. We're told it's bound by the line y equals 4. And just to zoom in on the line y equals 4 for a second, because I feel like this really helps my students. So what does that mean? That just means when y equals 4, like, why is that a line? Just to review some pre-calculus. When y equals 4, we're just saying that for all x's, right, any x is always equal to 4. So for no matter what x you choose, negative or positive, it's always equal to 4. So what does that end up being? That ends up being the line y equals to 4. And then a review from pre-calculus, y equal to x squared, right? We should remember that's just this bowl, y equals x squared. So we're told y equals 4, y also equals x squared, and we're told that, or it's also bounded by y equals x squared and the y-axis. So this is the region. So that's the drawer face that we are going to pull out. Now, in my example here, I pulled it out along the distance of the drawer. When you're facing your mirror and you go to pull out your top drawer and get your clothing or whatever you have in that drawer, we're basically going to pull, instead of pulling straight out, we're going to go around the x-axis, right? So that means that this kind of in here, and this is like, this seems like it's belaboring the point or taking too long, but this is really what Calc 2 a lot is about, is visualizing. So that point is going to be empty. Okay, so if we were to imagine what that looks like, it's basically like some kind of a visualization of a black hole or something, right? There's this negative space in the middle where you could pour water into, and it kind of tends towards 0 at the middle of this circle, right? if that makes sense. So if we looked at it from here, if we flipped it over, which might be easier for us to see, there's something like this, and it goes in here and it goes to 0. So we are finding the area of this amazingly beautiful, idealized, complicated shape, right? Which has an empty space in it. So we found a way with simple integrals and calculus to find that. So how are we going to do that? How do we set up that that integral? Let's take a look at it here. So if we remember from the previous disk method, right, we're just going to take f of x and square it and integrate it pi dx, right, from pi r squared. So what does that look like in this case revolving around the x-axis? So we're going to take this function, y equals 4, and it's really important, and again, this is where students get tripped up. So y equals 4 is the same thing as f of x is equal to 4. And we should remember that when we integrate a constant, what is that equal to? And so this is just Calc 1 review, right? We're going to take the constant, take it out of the integral, and that's equal to 4x, right? Because the integral of 1 is equal to x. And then you have your bounds also, right? From A to B, evaluated from A to B. Then maybe that makes more sense. Okay, so if we know that, then it might not be as confusing to put 4 minus whatever our function here is, x squared. Okay, and then we're going to square these because these are basically radiuses dx from, and what are our bounds on the x-axis? And this is key. So can we find our bounds here? So we know that 4, we're told that in the problem, but when does our f of x, y equal x squared, intersect 4? And so that's pretty straightforward. So we want to know what is y, or what is x when y equals 4, right? So if y equals 4, and we're talking about positive numbers here in the first quadrant, then x is going to equal 2. So that helps us see that our bounds are 0 to 2. And don't forget pi. Sometimes I forget this. So this is the equation. So this is the correct way to set up finding this beautiful shape here that we revolved around the x-axis using the metaphor of a chest of drawers, right? Instead of a chest of rectangular drawers, we have a chest that has a shape like, I guess, like this, that we're going to pull out, but we're actually, instead of just pulling it straight out, we're revolving it around. That's kind of like part of the beauty and the incredible nature of this section of calculus. Okay, so if you've gotten to this point in the video, you can take off from here. But if you want to just go over the actual algebra, which is, and this is, many teachers will give you most of the credit once you've gotten to this point. But if we were going to do the algebra, what is this? This is 16x minus the integral of x to the 4th, right? And these are 0 to 2, and you've got a pi here, and you got to evaluate this, right? And you have pi here. So I'm going kind of fast here because, and this is a very sloppy looking way of representing this, but I think you get the idea. So we have 32, we have pi on the outside, minus, so this is x to the 5th over 5, right? Evaluated from 0 to 2. And that ends up being 32 minus 2 to the 5th is 32 fifths times pi. So this is a number, right? And your units would be cubed. I guess that's like a really good thing to point out. What are the units of this? Like we're making a volume from an area. I think it's really important to just keep reiterating that. We're taking an area, which would be like meters squared, and we're converting that to a volume, right? Which would be meters cubed or cubic liters or whatever, right? We're making a length times width times height situation, or we're making a sphere, however you need to think about that, about a volume. But in the end, this is the solution to the problem.